before you start.
Magnitudes.
2 should be the largest.
3.
Yeah, 2 should be the largest.
2 should be the largest.
And why do you say that?
Because the index difference will help confine light to the center and make sure that we have a balanced mode.
You can get total internal reflection. So
I think the book said it was kind of like basically it's kind of like a bowl, and the light stays in the bowl. It's not like that. It's like a gravity well or something. I don't know. It's
it typically stays in between.
Yeah.
What book says that?
The Photonics one.
The
I have the book.
Yarivan?
Yeah.
Says that?
Something like that. It didn't say that it was like a bowl, but it was like
basically
kind of like electrons.
It keeps it in between.
Yeah. That's what I was getting at.
Total internal reflection.
Yeah, it keeps it within.
I mean, and then in quantum mechanics, there's this with the energy. So you can think of a particle, but here we've got a positive.
Yeah.
So okay, which would you want larger, epsilon 1 or epsilon 3? Epsilon 1's larger than 3?
Mm-hmm.
Which is so then epsilon 1.
I think epsilon 1's smaller.
No, it's bigger. Epsilon 1's bigger.
You can put anything you want into a waveguide or
you
when you draw the picture.
Oh, okay.
These are very
Yes.
okay. So, what are the solutions? So, I'm assuming that you can derive this equation from Maxwell's 4 equations and play around and get this equation. And we'll consider the TE mode.
Sorry.
This is a good one. So, in this case, if beta squared is greater than all these parameters, what type of solution do we have?
Beta squared is greater.
Huh?
Certain times. I think certain times.
3 times? What?
I think if beta is greater, it's just
Both
exponential.
one side.
I think because I have it graphed out, if this is 0 and this is beta, as you go forward, it becomes exponential.
So, can you prove it to me by solving that top equation? Here's you can use a bunch. You can if that color's good, you can use blue.
Yeah.
But sometimes
we're looking for a solution.
where beta squared's in that. Look at the top equation.
Yeah.
Yeah.
So
So
if
beta squared's greater than all those.
So then this term is always negative.
Okay.
And the solution to make
What is right? EY of x equals.
e to this times x.
You just call it h or some variable.
H. Okay.
There.
But then I'll set it equal. Okay. Where h is equal to psi.
Okay.
Isn't it square rooted?
Because it comes down to us.
Oh yeah, it comes down.
Do we need the imaginary here?
Oh, wait.
Yes.
Oh, we need this.
Because
Oh, you can just include it in the h itself.
when it's
That's what I'm
bigger
asking.
than this one, this will become imaginary. So
You're right. You're right.
Yes.
Okay. So this is that, but because beta is greater than this is less than 0, which means the square root is imaginary.
You brought it. Yeah. Just go ahead and show me. Just show me. Once you get EY of x, now you can. Once you've read out the most general expression for EY of x, is that the most general expression?
Maybe with some magnitude.
I think you need the I.
You need the I. No, because he's right. The I comes when we're looking at a specific solution for H. We're just saying that H is equal to this, but if this is less than that, right?
Well, we're going to be increasing beta.
Huh?
We're increasing beta, so beta will be greater than.
Yeah, so beta is greater, but we're subtracting beta.
Won't you get a square root of a negative number?
Exactly. So that's where the I comes from.
They cancel out. Because
Right,
there originally is an I there.
Square root negative.
What I'm saying is, if you want it to be exponential, like otherwise you're going to have an oscillator. It's going to oscillate. It's complex.
It should not oscillate.
And I'm saying it's just an exponential. I don't think it oscillates.
You're right.
Like you need the I to cancel out, because when beta gets super big, this is going to already have an I in it, and then this is going to be big. This is going to be complex, and so you need a complex number to cancel out that. That's what I think. Does that make sense, or am I getting something wrong?
Yes. Yeah.
Well, what's the general solution?
It should be some magnitude times e to the.
Well, why don't we plug that in and see what happens?
Like this?
Take,
These?
well, yeah.
Yeah, so like
Plug-
the D squared, just plug.
Take the first derivative of that
Just-
and then
yeah.
take the second derivative.
DFS.
Alright,
Just we gotta do the first to start.
Sure.
So that'd just be
Bring it down once.
AE to the negative IH, I guess.
It's negative I H e to the negative I H. This is our first derivative.
Okay.
We'll have to see the second derivative mostly.
And d dy is d squared divided by x by dx squared is equal to still a minus
So
Now
it's
it's
squared, and so then it'll okay.
plus
Minus
and
e,
minus.
yes.
So negative is the
Yeah, we just do it squared though.
Sure. Like you want negative
Yeah,
IH
negative I
squared.
to H squared. So that it basically just cancels out to minus H squared.
Negative IH x.
So then that'd be some
So
constant.
that's our second derivative. And if we now plug in the h value that we found,
Well, so you're gonna
That's gonna be equal to H
Is that-
squared.
you get care of the minus sign in the I.
so
So then yeah.
negative squared and then I squared, this just gives us negative h squared.
Yeah. And so
Well, wait, I squared is negative 1.
Yeah, but
yeah, so that's
that's
Yeah.
the negative there.
Oh,
Because you square the plus or the minus, you get a plus.
and then you do yeah. And so then from there we're able to just plug in H for that, like that thing squared. That'd just be E to the I,
Okay,
okay.
let me find the negative. A,
might need to move your
and then h squared is what we have
E to the
here.
I, yeah. So then let me simply E to the I.
Yep.
Can you
I,
make this sit up more?
E naught
I
squared
can't get
minus
this.
mu naught squared
Yeah, I'm just gonna and the
Can I
IT
leave
for
this
the-
h just as h, the
Mhm.
exponent?
Pardon?
Can I leave the exponent in terms of h, or should I plug this in?
We could leave it in terms of
Just H.
I guess. And
This is our second
And then
derivative
we
of
can-
dy,
okay.
which
And
that
then
cancels
also-
out because
also
this side's positive.
one more thing too, we can reorganize this because we already established that E to the Y of X, E to the negative H of X. So this is the equivalent of E squared is beta squared minus and then just times E of Y.
Yeah.
And then since we already established this equation before, if we took this over to the other side, we can rearrange this as second derivative of E of Y X is going to then equal minus I k squared x, and those two are equal.
So you said you're bringing that over.
Yeah, and so I'm just demonstrating that that if we solve it this way, this is equal to that as well, and so that proves that it is that our math worked out. Well,
So,
it worked out correctly.
But your electric field, if we went to plot that, e to the I theta is cosine theta plus I sine theta. So you're saying you've got an oscillatory solution. Before you were saying it should be exponential. But so what? I mean, do you still say it's oscillatory?
Maybe.
Let's beta is greater than x.
Wait. What if we switch it around? So instead of saying e to the y x is equal to a e to the negative, we can just do e to the y of x equal to, let's just call it b for this case is negative h of x plus c e to the h of x.
Yeah.
We solved it like that.
Yeah.
I can only exponential
And both
instead.
types are valid.
Yeah, I know. I'm saying if we let's say that if we replace this with that, I think maybe we should get exponential instead.
Well, what you've written down, if you were to plot that, that's exponential.
Yeah.
But if you have the I there, you've got sinusoidal.
Yeah, so that's what I'm saying though, is that because these are basically equivalent.
Oh,
Not basically.
No,
equivalent,
if
yeah,
they're
but it's just,
well, one's going to give you oscillatory, and one's going to give you exponential. So
Yeah.
they aren't equivalent.
yeah, so I think we should go with this one because it's supposed to be exponential.
Well, why is it supposed to be that? I guess that's my question. Is why is it exponential, or why is it oscillatory? Why is it exponential?
That's what the book
Yeah.
The book says it's supposed to be exponential. That's why
I
we're
mean,
trying
the
to.
book just said whenever beta is greater than all of them, it's exponential, and it didn't
But
have any signs or anything.
If you look in the notes, I looked at that case, and I don't think the book said that. I think it did the same thing that I said. I mean, yeah, I guess I was surprised. When you here, the way I look at this, here, this is beta's larger. This is negative. So that tells me, just that. Okay, the second. I'll just use y. Since this should be partial x squared. Okay. Partial plus. This is going to be negative. So minus c times y equals 0. Or the second derivative of y, I guess it's partial, is equal to a minus c times y.
Yeah.
So
What is positive cy in this situation? You're putting it over.
this is negative, right?
Yeah.
When I bring it over, and this
It'd
is
be positive. Yeah.
Wait, this is negative. And so this is positive
Yeah.
c times y. So if this is positive, then if I assume the solution y equals a e to the, let's see, I'm going to say cx plus b e to the minus cx, and then I get square there. But I take the first derivative, brings down, this, I should call that c squared.
Well, yeah, that's.
But c e to the cx plus c minus c b e to the minus cx. And I take it again,
Be c squared.
bring it down to c squared e to the
Cx plus c squared. So that-
and this is going to be plus when you take the next derivative, I get c squared e to the so this comes out to be the c squared e to the c squared times y. And so
What are you calling C?
I think it's H.
this is c.
Yeah, so it's our H.
It's just a constant. Yeah, you can call it h. You can sometimes I call that. All I'm saying is that this is just math. It's not nothing electromagnetics.
Mm-hmm.
But to get when this is positive, I need exponential solutions to satisfy.
Mm-hmm.
So does this just mean that it should be sinusoidal in all four regions?
Exponential.
It means in this case it's exponential.
In all four regions.
Mm-hmm.
In fact, that was my next. So my next question then would be, we're looking at the solutions. What do this? We're going to do all cases. So here's x, and if my solutions are exponential, and of course the c changes with in all of these cases it's exponential, but the c value changes, so the exponential decay is changing in each layer. So maybe someone draw
You know what John said?
what.
I think it's flipped. It's the 3 on the top. Is this
Wait.
This is positive x.
Yes, that's positive x.
I just want.
And
This is beta over here.
no,
So,
I mean-
wait, no, that's C. Sorry.
wait, what do you? Oh, this direction. Okay, this is propagation. Well, yes. I think let me do this. Okay. This is x, and this is z.
That's what it's trying.
Propagation.
You say in3 was the smaller one?
E3 is
It's
the
right
smallest
above.
one,
Look
yes.
up there. It tells you what
E3 is the smallest. Or no, it's the greatest.
epsilon 3 is.
That's supposed to be the smallest. That's
But
greatest.
they're all less than beta.
Yeah.
So it'll be the same behavior.
I think it. I'm just trying to make sure I got this the same as my notes.
Well,
I
forget your
don't.
notes. Yeah, please throw it out the window. I mean, don't. It's not the same notation. I mean,
Yeah.
and I want to see the thought process, not finding something in your
Where's the
notes.
equation? It's this one? No. It's that one. I think it's gonna be this one's the smallest. As x increases, I think it's gonna get smaller.
Oh, so let's discuss that. Where is the largest exponential damping going to occur? Which layer?
The damping? Large damping?
I don't
What-
think so.
the-
They're gonna be the
Sure.
Where is C the largest? Or where's it going to go? Where does it exponentially fall off the fastest?
I think this region.
Yeah. Because that's where we get the biggest difference.
Everyone agree?
Yes.
Jay Shen, you agree?
Well, in fact,
I think it's like this.
in fact, I still little difficult to understand
You what?
what's the situation now, the bound or radiation.
What we're looking at.
Yeah, you make the
Let me say this. This is the electromagnetic wave equation
Yeah.
for the electric field, and I'm looking at what's the mathematical nature of the solution.
Yeah.
When you made it, doesn't have. I don't care. You forget about bound or
Yeah, because
radiation.
because-
I don't care about bound or radiation. I just want to know mathematically what are the solutions.
So we should consider the equation to plot it, right?
Pardon?
We should according to the equation to plot it.
According to the solution to the equation.
Or
what
solution
are
or
these?
equation. Yeah. But
I'm gonna erase this. That should have, should have had two terms, A plus B.
Yeah.
And anyway,
With the positive and negative.
yeah.
Yes.
Try.
This is 4. I can get this reversed today. Oh wait, it's out of order though. I was thinking.
That's fine. I think, I don't know, I just would have thought that it would come back up and then say this isn't a solution because it requires infinite energy. So we would have something like that.
I agree. I think since E2 is gonna be the largest of it, I think it's gonna get back up here. It's terrible.
Oh, this one?
It's fine. I'll do another color just so Doc doesn't tell us if we're or I think it's gonna come back.
Oh, you're saying it's a practical solution?
I think so.
No, I'm saying, I'm just asking for mathematical.
Because
Mathematically,
here's my logic,
it's
right?
like this.
Because E2 is gonna be the largest, right? So in theory, this would be steeper because it's the smallest of them, right? But since E2 is gonna be larger than E1 and E3, wouldn't this be the lowest point? Right?
But then wouldn't energy count? I don't.
Here, you're doing two types of solutions right now. Because Dr. Evans wrote out that EY x can be A times E to the negative CX plus B times E to the positive CX, right?
Yes.
So we have two types of solution. One
Oh,
of
I
them
see.
is going to be like damping off, and then the other one is what you've drawn where it's like increasing.
Yeah.
Right? So
it's
right
two.
now, this is a combination where it's increasing, but then it's damping on the other side.
And so then also at the same time, if we want going the opposite way.
Right. But we can also eliminate this type of solution because this requires infinite energy. This is telling us that as we leave our waveguide, our solution gets more and more energy,
Which can't happen.
which can't happen,
So I mean, we can
I think.
think.
Oh, so we'd have to do something like this?
Well,
Like-
I think we can say
Well, that's what
we say equal to 0. Yeah, we say equal to 0. It will be A. It will be B. So we can find the
Yeah,
yes,
you
we
can
can
find
find
that. That's where
yes. So
the boundary condition.
yeah.
So I think it is this
Go back.
one physically, though that is also a solution, and what you drew is also a solution.
This is like 4 solutions.
I mean,
Yeah,
it's
I mean,
combining.
we're mathematically.
Hear me out.
Yeah.
I'm not.
Could be
Then there's the
redrawn,
what can you realize physically?
It look like this then. That'd be the correct combination of those.
Any combo.
Right. Yeah. Well, right. So let's see. What did you draw first?
Oh, I
This
drew-
was
I
your-
drew
This is
that.
what you drew.
Yeah.
So, this is e to the cx, and down here, let's see, this is c3x. Here it's e to the minus c1x. And in here, the most general solution is e to the c2x,
2x.
an a plus a b, and left off the coefficients. E to the minus c2x, because it can go both ways. But in the general case, you also have a1, b1, e to the c1x here. So you can have one or the other. It can't be both. It either has to go to 0. You need this one because x is negative, what you drew here. So there's multiple choices here, but all your choices right here are going to go to infinity. Well, you start off here, but you could also have it decaying exponentially here, like a3 plus b3 to the minus cx, c3x. So there's multiple choices here. But you could also have, and decay constants are different, so you can have something like this that doesn't go to infinity. So is this a physical solution we can have?
I believe that's a
It's like 4 solutions.
You could probably summarize it into 2. I think we give this is definitely one. I believe we have
The general type.
the general type, and then I think we just do combine these into one. So it's the general type with that exponential.
Well, all of these, I thought I just argued, these type of solutions are all going to have some exponent that's going to infinity. So we can't have something that's increasing on either end here.
So it would just be
So not these.
Yes.
yeah. So then it'd just be that.
But when you have it all, okay, so
They work mathematically.
wait, no, you could leave that there. The question I'm asking is, what do the solutions look like? And what we're saying is that these aren't allowed because we don't have infinite power.
So these are mathematical solutions, but you can't actually have them.
Well, we don't have infinite power. This has a
Yeah.
because we don't have infinite fields.
So if we're gonna do it, this is mathematical, right? And then this.
All of them are.
And then something like this might be. That's kind of not really what I'm like. Maybe like this. Kind of.
It'd be like that. I think. I argue it'd be exactly like Adam drew, like this. It was very similar.
You do
Yeah,
have
I'm kinda not-
exponential there.
I'm not really an artist here.
So
Okay.
that's really this one. Where
Yeah.
You've got exponential damping maybe and exponential decay. So this doesn't violate the infinite power.
Yeah.
But, and so you think this is a solution our waveguide could support?
I think it is.
How about you? You think,
Well, I think right. Yeah.
Like this makes sense, but we can't have this physically.
Yes.
Unless we have infinite power, we would be
This
able to
is
achieve that.
going up, this is going to infinity.
Yeah, we can. This is just mathematically. You can't actually have this.
Well,
So
it's
then-
impractical. In theory, if we had infinite power, we could, but we don't have infinite power, so we won't be able to achieve that.
Well, yeah, I'm not sure if you want me to leave it here as a
Yeah,
representation.
you could leave it there as something that doesn't work.
That's why it's
But
dashed. That's what we actually want.
But I still have, I think you all agreed that this one,
Yes. Yes.
so, this one actually also can't work.
Because of the slope response.
Well, where does the power come from in this one?
When, if you have a waveguide, you have a laser, you shine the power in. But the problem isn't the power, the problem is that a solution that is exponentially growing would take infinite power. So there's a reason this one doesn't work. Yeah, but why, basically, not, the electric field has to be continuous, but its derivative has to be continuous. Why does its derivative have to be
Because it
continuous?
reaches zero.
Changes directions.
Hmm?
Like,
What changes it?
well, the slope.
Yeah, but why can't it? Why do we require the derivative to be continuous?
Because the magnetic field needs to be continuous,
And
and that's related to the derivative.
right, yeah, so, H, if this is TE, so HX and HZ are proportional to the derivative of Uy with respect to X. And these have to be continuous.
Mhm.
So that means this has to be continuous.
Yeah.
So all of this is to say that this case can't happen with Maxwell's equations. So, this,
So there's no solution.
what do you,
What?
huh? You still have,
just repeating what it said before.
huh?
I was just repeating what it said before.
How much did you pay for the book?
$30.
Huh?
About $130.
Okay.
Look, I know all college books are a scam, but
No, I think what I'm about, okay, so now tell me what happens if, we have epsilon 2 k0 squared is greater than omega squared, which is greater than k0 squared. Epsilon 2, this should be 3. 3. k0 squared. So what does the, now the question is, what does this solution look like?
I think it's just
What if you just
I
Well,
think it just oscillates inside.
okay, I want you to show me, prove that to me, like you proved maybe the exponential.
I'd be honest. Maybe.
All you do with it.
I might.
Oh, no, don't draw it there. I want you to give me the wave equation, show me how you get a sinusoidal solution. And then, once we all spend some time,
Okay,
then
so
you can do this. But start here, tell me what this is, and show me what the mathematical solution is. Show me whether that's exponential or not. Is it still exponential?
I don't think it'd be exponential.
But show me why it isn't.
This is what I had.
What are you telling us here?
The two situations. So in this case, it will be real. But in this case, it will have real and imaginary. It will be complex. Yeah. Because you can see if we take a square for it, it will imaginary part.
I agree.
But where does that happen? Oh, because one is constantly.
And epsilon 2.
Yeah, that's what I was getting at.
Yeah. So in this
That.
case,
Yeah, no.
Oscillate.
so in this case, it will oscillate in the core layer.
Why will it oscillate in that case?
Yeah, because in this case it will not go to 0 or 0. It will just
No, wait.
adjustment. We have 2 layers. Yeah.
I didn't. See the wave equation up there? Show me what's the solution to that wave equation?
This.
Yes.
Wait here.
So write out EY.
I think let me be. Y is equal to A.
But how are you going?
I'm getting this because.
Is it just X?
No.
H of
no,
X.
it would be H of X.
H
No,
and
why don't you erase it and write it so we can see what you, yeah.
So, you read it would be UI. Y is equal A B sine of H of X because it'll be real in this situation.
Because what?
It'll be real in this situation.
H is, in this case,
we're gonna have.
epsilon 2, so it's, you're defining what I call C up there.
Yes, the
Your
C and
H,
H
and
are
that
equivalent.
H is positive.
Yes, I can replace it real quick.
Huh? No,
Oh.
leave it H, that's
Okay.
fine, no problem.
Yeah, and so since.
Okay, now take the derivative, first and second derivative.
I don't have a
Correct.
Wait a second.
No, I was just double checking my notes. I have my notes on my phone.
Okay,
I
And so I'm just making sure my math is correct.
Okay,
And
so
so
y
then-
of x.
I think it's derived from
X
this.
is going to equal sorry, a minus a sine
More complicated.
h of x plus b cosine h of x. I've got to have the h here.
Good.
Minus h of a plus h of b, and then we take the second derivative. Squared, which is then equal minus h squared sine h of x minus h squared. This way. B sine h of x. So that would be the second derivative right there.
Okay, so what's, now, why don't you
Factor it in.
not out, but if you bring the h squared minus h squared outside,
Yeah, so then
and then you've got,
you can also take it as just as a minus h squared, not even just h, and then be a cosine h of x. This is why I started typing stuff out. It only got worse. H of x plus b sine h of x, which as we
It's
here.
not h of it, it's just hx.
and so then this is going to be the equivalence of also equal to minus h squared of y. That would be step squared.
so
And h squared is
this is what you're calling h squared?
Yes. Yes.
Okay, I mean, this is h squared.
That is h squared. Yes.
This is minus h squared, so that it's 0.
Yes.
So this is the solution
This is the solution.
Okay, we're looking at this case.
Mhm.
This is the solution in layer 2,
Mhm.
right? What about layer?
With layer 1
One
and
and
3,
three.
it'd be the same situation as before, I argue. Right?
well,
1 and 3
we
would be
said it has to be less than 0, right?
What has to be less than 0?
Or wait, no.
No, I think for these two, it'd just be the same as last time.
No, I'm referring to his thing.
Oh, yeah. But
Unless
no.
it's wrong.
Remember our math previously?
I don't know what this, I mean, this is the way to do it.
Yeah, no. This is he was explaining that this is the second one, so this is the real solution. And then for the E1, E3, it's gonna be the same as last time, like our previous way we solved it, because it's
So
still
this
complex.
is negative.
Yeah, that's what it is.
Negative, not con.
Yeah.
Okay,
And so the way we find E1 and E3 would be the same way we found last
okay.
in the previous scenario.
Okay, so why don't you derive that solution?
So in theory, it'd be going the same direction here and here. So then it'd still be boom there, but then it gets real. So then I think you go something like that. It's big size English. I'm also not very good at drawing.
Okay, but,
Yeah.
so you've got oscillatory solutions in the middle,
Yes.
exponential outside.
Yes.
Yeah.
So all the bound modes satisfy this case.
Mhm.
Okay, so
Yeah.
now, let's do it where this is epsilon 1,
It's like 2 now.
k0 squared. This is beta squared. Now, what do the solutions look like?
Alpha is anything one.
Well, then it'd be the same math here for the E2 and E1, which means that it'd only be exponential for E3. So in theory, it'd just be
Why don't you draw what?
It would just be the same thing, but it's
Type of it.
well, yeah, it'd be the same thing, but it's just exponential. No, not the same thing. It'd be exponential here and then oscillatory here,
do like this, and
and
then
that's just keep going.
pardon my terrible.
Yeah, but that's just keep winding. Yeah, exactly.
Does everyone agree?
I agree with that. And so then if
Well-
beta, sorry, man.
Go ahead.
I was going to say then that in the same train of thought, if we have these two switch, because I assume that's where we're going next,
Yeah.
It'd just be oscillatory for
Before
all.
okay, but now let me ask you, which between epsilon, what you've drawn in layer 2 and layer 1, which are those the same oscillation frequency? Do they have the same wavelength, those oscillations?
They would not know.
Which one would have the larger oscillations?
E2 would have the E2 would have the larger ones.
The period would be longer?
No, E1 would be longer. E1 would be
Why?
because E2 K naught squared is going to be larger than E1 K naught squared, so therefore it's going to be.
Wait,
I'm just saying
your H?
their H, yeah, the H is going to be larger, and since since the
so it's HX, and we're saying that you're right. E2 for E2, then H is large. I guess H2 is larger than H1.
Well, now you're talking about the damping.
Well, even in here, what it is that the H2 is going to be larger than H1.
So if H is larger, does that mean the oscillations are faster or slower?
It's going to be slower because that's going to be a bigger wavelength, right? No, man, I'm missing it up.
Yeah.
Would it be the opposite?
Yeah. If H is larger, then the oscillations happen faster.
Why?
Because it's it's just it's taking you through the unit circle faster, right? This is like a wave vector.
Let me ask you to plot cosine of 5x cosine
Oh, yeah.
10x.
Sure.
Call this x or
So yeah, the 10x is going to be
what?
It's going to oscillate more frequently.
2 pi over 5 is our period for the 5x. So,
And that'd be 2 pi over.
but then the 10x, the period is 2 pi over 10.
Yeah, so then it would oscillate.
For cosine.
So then
Okay, that's fine.
So
You
then-
can change it to
yeah,
sine.
so then
I'm
E2
fine with sine and
If
sine.
E2 is greater than E1,
There's
then
a
it
phase
oscillates.
shift in there.
Okay.
That's
So
all.
there's
Since E2 is going to be greater than E1, it's going to oscillate more frequently.
What's going to oscillate fast?
In E2, it's going to
Layer 2. It's gonna-
layer 2, sorry.
Okay. So I'm going to draw layer 1 with a longer
Yeah.
oscillation. Okay. And then the other case,
The worst.
when this moves over here, look, where are the oscillations?
So
It's going to be.
Or what are the solutions, I should say?
So then E3 is going to be very, very long. They're all going to be,
Say,
and they're all going to be represented in this.
okay,
but-
why don't you draw it just for
Okay. Instead of just making everything extremely long, I'm just going to do it. Like slightly.
So that's arguably something like that. But
Yeah.
wasn't there a homework assignment that asked you to do all these? Okay. Okay. So any questions about?
No.
This is what always gives us, I don't know, the case here. Okay.
I think I just got confused on this. Even on the first case, because I was thinking about this instead of the
It's all
terms
recorded.
that pop out
Oh,
of the
okay.
derivative. So I flipped it.
I mean, it's going to be like inverted in the recording.
The first case, so we've got the mathematical solutions, and then we've got the ones that actually happen.
But none of them actually happen.
Yeah,
One side is you can't have it because it's infinite energy, and the other side you can't have it because there's a slope discontinuity.
It's a derivative.
Yeah,
In quantum mechanics, the wave function psi has to be continuous and its derivative continuous. that's why every problem you solve in photonics like this there's an analog in quantum mechanics. So let's see.
Next time I'm gonna print it out.
If I print it out, it's gonna be like 10 pages long.
That's fair.
So all this index profile. This is still a little moist.
You want a better marker?
I think it's because there's when I wipe this down, it's
Oh.
still wet. Here. Okay, so this is X. I'm going to call this input. And I'm going to say that what I could do is I could divide this through by K0 squared. K0 squared, but then I'm going to take the square root. Oh, so that means the square root here. Square root here, square root here. And this beta over K0 is really what we call the effective index, right?
Yeah.
Okay. So let's say the effective index, we choose the effective index to be, I guess here. I can change this. And so we have now to first identify which regions are oscillatory and which are exponential.
What do you think below the index is going to be exponential?
Yeah.
Well, just based off of.
Why don't you mark in green what you think
So, yes, I agree with you or not. Anything above the effective index is going to be oscillatory, anything below is going to be exponential. So, because of that, and then obviously the more above it is above the index, the more times it oscillates.
So first let's identify the exponential and oscillatory regions. Then we'll come back and ask.
This is going to be exponential. This is going to be oscillatory. This is going to be oscillatory. This is going to be exponential, and then all this is going to be exponential.
So let me region 1, 2, 3, 4, 5, 6, 7. So which?
Well, one's going to be exponential. I'll just do EXP for this one. 2 is going to be oscillatory. 3 is going to be oscillatory. 4 is going to be oscillatory. 5 is going to be exponential. 6 is also going to be oscillatory. 7 is going to be exponential.
I'm confused. So you drew it all as one thing, but the x-axis is just
that's
line,
the index
right?
profile. Instead of having this is a 3-layer
Oh,
structure.
I see. It's just
Yeah.
damn.
This
Yeah.
is a 9-layer
Yeah.
structure.
That's what I'm arguing.
I was confused by this.
Yeah, so
So that's the bottom. That's here.
I couldn't see it from there.
What if this is 2.9 and this is 3.7?
Okay.
The index.
Yeah. And so region 1 is going to be exponential, 2 is going to be oscillatory, 3 is going to be oscillatory, 4 is going to be oscillatory, 5 will be exponential, 6 will be oscillatory, 7 will be exponential, 8 will be exponential, and 9 will be exponential.
What is the red line?
That's the effective index.
That's the effective. That's
Or the effective
Oh,
index.
so it's just beta over k naught.
Yeah.
Oh,
yeah.
yeah, that makes sense.
That's more.
So it's literally just what you told me, right?
Yeah. So you want me to graph this as well?
Well,
Like in
before
theory?
we do that, which area has the shortest wavelength or the shortest period?
This will be the
Should be the
shortest.
one with the highest frequency, right?
Well, yeah. But when I would draw this, I look at the period,
Mhm.
period of the thing.
Yeah, because remember when the
Okay. Why don't you mark the ones in the order of fast of the
Fastest to
the
slowest.
period, the increase in the period.
So this, that,
I need 1,
this, that.
2, 3, 4, and then everything else becomes
Everything else. Okay, we could use maybe black to say which one has the strongest damping.
Strongest damping
Well,
would
yeah,
be this or would it be that?
Are we counting this?
That's the outside.
It'd just be
Yeah.
the base,
That's
right?
the outside.
Okay, and this will be
Because the exponent gets the furthest from 0.
Well, I just wasn't sure if we were counting
why
those
not?
two.
Yeah, it has to go. So, I mean,
that'd be the order.
that's the last layer. The first and last layer are always infinite.
Oh, this one too. What are we at?
Oh
like
yeah.
4?
Oh,
Is that, what is that?
okay. So I was.
3?
Yeah.
There's a reason I was forbidden to put in handwritten notes.
1, 2, 3, 4. Okay. Okay.
This biology doesn't take your handwriting.
So, is there anything different between region 5 and 7 than in the solutions in 1 and 9?
1 and 9 should be the same, right?
But, 1 and 9 have the same exponential damping. But is there anything that's different between 5 and 7 from the general solution?
5 and 7.
The general solution for.
Thanks.
Okay. Well, once you draw a line below it, and you could maybe write in a possible solution now that we know how things should work.
Actually, is anybody else want resolutions?
I mean, you're the shortest one here, so.
Oh, come on. I'm not the shortest one. Yes, you're just BFG at 6'5", but I'm not short. My hand's back here. I almost made the graph with the screen.
Okay. You want to?
Yeah, let's do. I kind of do that terribly.
I was gonna say,
Yeah.
drop these regions down.
Also, just put this like that. So I can look at the shorts. All of the similar heights. That's true. There's more short people than there are tall people in this room, Sam. So be careful. Goodness. So, we'll argue that it's gonna be like it's the start
That's exponential.
exponential.
Yeah, but it should curve the other one.
Wait,
No, it's like.
yeah, I can't curve up because that's
Yeah, that's what I
when you have
thought, yeah.
infinite energy.
You're right. You want it to go to 0, but like you were going off. Like this is the 0 line.
Yeah.
So you need it to come towards 0
This
as
is
you go.
2.9.
along.
Oh, wait.
So it's either
So
that
that's-
or that, depending on what you draw for the next one.
And then I was just gonna go.
No.
Yeah.
Shouldn't that go around 0?
That's what I was gonna try to do. So would it just be? Are you saying that you just go like, and then?
Nah. It's
Well-
not like it just shoots up. It should go
You
like
gotta continue it,
maybe something like that.
except it's
That's the
gonna
thing,
be
though.
fast
This is supposed to be the most
oscillation.
fast oscillation. So.
Okay. But then
Oh, so then
do
it's
fast
okay. Yeah,
oscillations,
my bad. So
but-
then
It's gonna be like noise, basically.
Yeah, exactly. And then we hit the boundary condition.
Sorry,
Or in our next
but to slow down slightly.
Yeah.
Just imagine this is like a lot more drawn out,
This one's
and
even
this one
slower.
here is just gonna be super slow.
Yep.
Then once again, it's gonna go, but it's less.
Well, you only want
You
you
don't
want it anywhere where your exponential decay. It should just be decaying to 0.
Oh, the king. Yeah.
Well, you don't want to go clear to 0.
Yeah,
Because
because it's gonna
got
get
an
taken
energy.
to the next.
Well, I-
Yeah.
That's it.
All right, out of here. You take over. We're the same height. I don't. Despite what Sam says, we're the same height. So.
Alright, so it hits here, the slope continues. We're decaying. Yeah, so it's not quite zero, but we hit the boundary condition, and now I guess oscillating pretty quickly.
Yeah.
And then
Oscillating again.
Oh, sorry, not oscillating.
Exponential.
Exponential. Zero. Never zero. Forever almost zero.
Yeah. Not the best graph in the world, but it works out.
One thing I'd point out that you might be aware of, and that's what I asked you, there's some difference. This is exponential, right?
Yeah.
And is there any difference between the solutions in these two regions and the outer regions?
This one should decay faster.
But other than the decay.
I mean, they're decaying from different directions.
They're decaying after oscillation.
The thing is, in these inner regions, in the outer regions, you have e to the minus, let's say delta x plus b, e to the plus delta x. But you threw away the outer ones. But in the intermediate regions, you have to keep both terms.
It could be.
Oh no! You keep both terms to match the boundary condition. You need those to match boundary conditions. Actually.
So in here, for one in the middle,
it actually could
come back up.
You could have it's exponential. No zero crossing, but it could come back up. Same thing here. It could be a mixture.
Okay.
I was just saying it'll oscillate while it's decaying.
Yeah.
I mean, when I say oscillate, I think zero crossings. That sinusoidal solutions.
Well, it'll be kind of wavy.
But it can come. It can come down.
Like
this slope might.
Like this.
That's an oscillation.
No.
Oh, that's a
He's saying it won't cross zero. It'll have.
It's not gonna have multiple humps. Because it's a sum of something decaying this way and the decay. They have the same decay rate, so it can come from both sides. Yeah, it really depends. You have to match the boundary conditions. So the values of A and B aren't. If these were the same, then you'd always have what you call the bowl. But A and B can be different because they match different boundary conditions. So you could put something like this in the waveguide, and then it'll find all the modes. Actually, there'll be a the lowest order mode of this, and
It's basically what you drew at the beginning, where it's like that bolt. Remember?
Oh.
Except this time you're not at the edge, so it doesn't go into infinity. It just goes
in
to
the middle. But you have to allow in the intermediate regions, just like in these regions, you have the equivalent. You have two solutions for A. You have a sine and cosine and all these things. We're pretty much used up our hour. Any other questions?
Did we cover everything we were supposed to cover? Or?
Yeah.
So the first thing's impossible. That's never happening.
Yeah. What if beta over k? If the effective index is up here, or if beta over k, it's not a physical solution. It's not a solution to Maxwell's equations.
Mm-hmm.
Okay.
Yeah.
So basically, I guess it was at the written midterm where you're asked to do this, or was it a homework problem?
I don't know which one it was. I remember doing this.
You don't remember?
I remember doing this. I just don't remember which one it was.
Like the question those over there was a homework question.
I can't.
These, yeah.
Yeah.
Right. This I didn't do.
Yeah. But it's just an exception.
This is an application.
I did this before.
So when you see a waveguide, there are waveguides like this, and in fact, a simple example is where we did the coupler, right?
Yeah.
But you can do a coupler where it's asymmetric, and some of the laser structures we've made in the past with gratings and other things look like that.
Okay.
But, maybe, I don't know if it was you, Adam, that said, the question, can you do this with one waveguide, or do you want a waveguide for each? And you could do either way, but, it's easy to do with one waveguide.
I used three.
Huh?
I ended up using 3.
Okay, but it's just a matter of, yeah, if you do that mode search with waveguide, you loop on QZ, it'll find all these leaky modes.
Yeah, while I was doing it, I was noticing. I was like, oh, I could have just done this.
Okay, so a week from today, write up what we talked about, and maybe try, when there's questions like,